Good morning, everyone. Welcome back to the channel Purnima today. And you're watching video lecture series on field theory, series number 3. And come, let's go into the new lecture series. Today, we are going to see about Maxwell equations. Come, let's go into the Maxwell equations. So in this, we are going to see first what and all topics we are going to cover in this video. First one is introduction. Next one is Gauss law for electric field. And the next one is Gauss law for magnetic field. And fourth one is Faraday's law. And next one is the Ampere's Maxwell's law. So today we are going to discuss on these four topics. Okay. First, what we are going to do is, what is Maxwell's equation? Here, what is Maxwell's equations? Here comes, yes, Maxwell's equations. Maxwell's equations, the equation describes the relationship between changing electric and magnetic field is known as Maxwell equation. Here, the equation describes the relationship between changing electric and magnetic field are known as Maxwell's equations. So here we can see the equations, the Maxwell equations are extents of know how work of Gauss law, Faraday's law, and Ampere's law. So how it works off in the three laws. What are the Maxwell equations are extents of known work of Gauss law, Faraday's law, and Ampere's law. The two form of each Maxwell equations, namely as integral form and differential form, that is what known as point form. Integral form and the differential form, that is known as point form. So Maxwell equation in the integral form governs the independency. So governs the independency of certain field, and source qualities such as charges and current associated with the region space, surface, and volume. Space, surface, and volume. The differential form of Maxwell equation, the differential form of Maxwell equations relates characteristics of a field vector, at a given point, to one another, character vector of given point to one another, and to the source destiny at the point, The Maxwell equations provides the mathematical background of a study of an electromagnetic waves and transmission lines and antennas. Finally, the application where it is in electromagnetic waves, transmission lines, and antennas. This is the introduction about Maxwell equation. Now, first entering into the Gauss law for field vector. So Gauss law for field vector. Here, what we are going to do is Gauss law for field vector. Here coming to field vector, electric field. This is about electric field. That is electric field I vector. The total electric flux crossing the closed surface. The total electric flux crossing the closed surface is equal to the total charge enclosed by the surface. The total electric flux in a closed surface, is equal to total charge Q is equal to the total charge enclosed by the surface. The electric flux to the closed surface is, the total electric flux is equal to total electric charges. The charge can be expressed in terms of the total flux. The charge can be explained in terms of change in the closed surface, change in flux. Charge can be explained in terms of change in flux. The change in flux, we can write it as change in density, magnetic flux density dx. Change in flux is magnetic density. So the total charge enclosed Q is equal to, the rho v and to dv. So rho v into dv, where d is the flux density. So d is the flux density. Then the Gauss law for an electric field is expressed as total charge Q. The flux can be written as in a closed surface, the total flux density with respect to the surface. This also can be with respect to volume. With respect to volume, we can written as in a closed volume of rho v into dV with respect to volume. Okay, this is what Gauss law for electric field. Here we can see what is the previous. Yes. Here we can see what is the previous relations of integral form of a Maxwell equation and the derivation for Gauss law of electric field. So integral form of a Maxwell equation derived from the from Gauss law of an electric field. Here to relate D with the del operator to convert surface integral into volume integral. Volume integral using divergence theorem. Here we convert the surface integral to volume integral. So surface in a closed surface, flux density with respect to surface, with respect to curl of volume. So comparing two integrals, we can say that we are so rho v equal to curl of flux density. Rho v equal to curl of flux density. This is what Gauss law for magnetic field. What I've seen is why the introduction about Maxwell's equations, and here the Gauss law for magnetic field. The Gauss law here, what happens is the Gauss law is the total flux crossing the closed surface. The total flux crossing the closed surface is equal to the total charge enclosed by the surface. The total flux is equal to total charges. Here the flux can be written with respect to surface. We are taking the total flux density around the surface with respect to surface. So this equation can be replaced. The total charge is equal to enclosed surface. Flux density is with respect to surface area. In terms of volume, rho v into dV. And therefore, for this, we are relating for divergence theorem, we are relating the surface integral with the volume integral. And finally, we are getting rho v is equal to curl of flux density. So today we have completed Gauss law for electric field. Next video, we can continue with Gauss law for magnetic field. Thank you.